Hello, guys. Good afternoon, and welcome to all of you. Uh, in this video, I'll be talking about nanotechnology. But before talking about the subject itself, if we broadly talk about solids, so we can classify solids into generally into three categories. We can have the solids that can conduct electricity, and we call them conductors, and we can have solids which cannot conduct electricity, and we call them insulators, and we can have some other materials which can have conductivity between conductors and insulators, and we call them as semiconductors. So you can have materials which can have conductivity. Once you apply the potential difference across them, the current will pass through them, and you probably classify them as conductors. And in case of insulators, if you apply the potential difference, there will not be the flow of current, and you will say that the conductivity of insulators is very, very small. In the domain of these different classifications, we say that the whole network is explained using Newtonian mechanics. Because if I take an example of a conductor, in a conductor, the electron has to move a lot of distances. The electron will never find a surface, and whatever the properties there are, the way there is conductivity in these conductors, they can be explained using classical physics, the laws of classical mechanics. But the story changes. The story changes when you start boiling down the situation of material from its growth point of view, from its preparation point of view. By merely making a manipulation, can change the properties of the material. And strangely, when we go down from a macroscopic state to the nano state, we strongly find that the properties of the materials keep on changing. And the field that deals with the properties of materials at that scale, at the nano scale, we call that as a subject, we call it as nanotechnology. Nanotechnology is basically it's the conglomeration of different fields of science. It has physics involved in it. It has chemistry involved in it. It has biology involved in it. All the fields of science are coming together and working out the problems of nanotechnology. So to start with, if I have to define the field of nanoscience, this field is a science when we go to the nanoscale of the material. We find the change in their properties. The properties of materials differ. They don't behave exactly the way they behave when they are in the bulk state. When they are in the bulk state, so by merely manipulating the atoms of the crystal lattice, or manipulating the molecules, or macromolecular scales, we strongly find that there is change in the properties of these materials. At this scale, the point is, at this scale, we are not able to see such changes if we take the material to micrometer level. The changes are there when we go down to the nanoscale. And certainly there is a transition. I mean, we cannot explain the properties that have been changing with respect to the bulk materials to the nano state by making use of classical laws of physics. No, that's not the story. The story here changes. In addition to the change in the properties of the materials, there a new science comes in action. The science of quantum mechanics comes in action, which probably explains the properties of the materials at that scale. So nano certainly means it means dwarf from Greek point of view, and 1 nanometer is equal to a billionth of a meter. So if you have a meter rod and you will break down it into a billion particles, the billionth of it will have a size of 1 nanometer. So, to be precise, if we have to talk about the science that falls in the field of nanotechnology, the dimensions move from 1 nanometer to 100 nanometer. So anything between 1 and 100, any material between 1 and 100 will fall in the domain of nanoscale. So the things that we will be investigating there, we will be examining, or we will be preparing new materials. All these parameters will fall in the field of nanotechnology. So, in addition to that, there will be there are the properties that keep on changing at this scale. So, anything that behaves like X when it's in the bulk state, it behaves like Y when it is in at the nanoscale. Now, this is a comparison to give you the brief idea about the nanoscale. You can see that the size of an atom is 0.1 nanometers, and or we can say it's 1 angstrom. And then you can see the double helix of DNA. It has a diameter of 1 nanometers. Carbon nanotubes, which we are very well aware about, who have conductivity is many-fold better than that of the best material that is available in the world, whose mechanical properties are very, very better than that of steel. So you can see the carbon nanotubes, they fall in the diameter of 5 to 10 nanometers. Then you can see the protein molecule. One protein molecule has an average size of 10 nanometers. Can have a size of a transistor 35 nanometers. Then you can see RBCs, the red blood cells, they fall in the domain of micrometer scale. And you can see the size of human hair, it is 150 micrometers. And finally, you can take on this scale to the size of a grain of a sand. The size of a grain of a sand is 10 to the power of 6 nanometers. So if you make a comparison between an atom and the sand, there's a hell of difference between the two sizes. And the same hell of differences lie between the size or the diameter of a DNA molecule and a dot of grain. Now let's take another scale where we can have a deeper understanding of the size that I'm talking about here. You can see that 10 to the power of -1 certainly it is the size of an atom, an average atom, or it can you can start with the size of water molecule. As 10 to the power of -1, then one nano glucose molecule, 10, and then it is antibodies. 10 to the power of 2 nanometers is virus. 10 to the power of 3 nanometers, you have bacteria. Then the cancerous cells, you can see the size of cancerous cells. It's between 10 to the power of 4 to 10 to the power of 5. So you can see that nanotechnology can have a very, very fundamental role in managing or treating the situations of cancer, where we don't have to undergo through very hectic process of radiation. And then finally you can see the size of a tennis ball is nearly 10 to the power of 8 nanometers. So this scale is just to give an idea about the nanometer scale. When we talk about the nanometer scale, what is the size of that scale that all the fields of sciences are working on, expecting new properties, expecting changes in the physical properties, expecting that they can enhance the efficiencies of these materials, expecting all outcomes at this scale. So this is what I was trying to tell you, that at nanoscale, the physical, chemical, mechanical, electrical, all of the properties, most of the properties keep on changing when we take down the material to its nanoscale. Than that of the bulk matter. That means if I'm talking about something that is a conductor at the bulk scale, the same thing may be an insulator when I'll take it down to the nanoscale. Now, this is the guy who proposed and who had a vision of making a mark in the field of science. The man who proposed that why can't we translate the things at the very, very small scales. So this beautiful man, Richard Feynman, he came up with certain questions. These questions had something there where the pupil had to come in and work on. But he came up with some kind of ideas. The ideas that he tried to simply spread among the intellectuals, where they could have a direction through which they could move on. So what this man said at that moment of time, it was 1959 at American Physical Society. What he said: why can't we manipulate materials atom by atom? So this was the most beautiful sentence. That why can't we try for all that technology that is required, where we can make the manipulation of atoms, where we can move one atom from one position to another position. So why can't we control the synthesis of individual molecules? Why can't we write all of the human knowledge on the head of a pin? Why can't we build machines to accomplish these things? So the basic idea was, the theory was clear there. It was clear that the things that will come out at this scale, the things will be totally different, and we can have a choice to choose the technology where we can enhance some properties which may have technological importance in our daily lives, and we can ignore the properties which are not suitable for our technology, which are not suitable for our society. So the force, the impulse that was given by this man in that conference was that we should look for machines. We should look for the machines that can do the job, that can make these things possible, that we can manipulate the atoms. We can if we are in a position to manipulate atoms, certainly we are in a position to change the properties of these materials. This nanotechnology can have a long range of applications, and we will be discussing about some of the important applications of nanotechnology. And not only in the field of science, nanotechnology makes its roots. The nanotechnology certainly has its importance in the field of medical science, in the field of agriculture, in the field of biotechnology. All the fields that have to accelerate certainly will make use of nanotechnology in their fields. Now, we generally have two kinds of approach in order to prepare these nanomaterials. So we can choose the top-down technique, or we can choose the bottom-up technique. So the technique is like that you will break down a bulk matter to a state where you can reach to its nanoscale. And the bottom-up will certainly it is certainly something that in which you are conglomerating the different atoms, making reactions between them, and developing some nanomaterial particles. Now, why does this happen? Why materials become different when we go back to the nanoscale? The very first classical way of understanding this problem is the ratio between the surface area and volume. Now, if the area exposed due to a matter is small, certainly it will make small reactions around it. But if you break down this material into small particles, you are certainly increasing the surface area. You can see from this example, you have a 1 meter cubical box, and you keep on making more and more cubical boxes. As you increase the number of cubical boxes, the surface area of the material keeps on increasing. And you can see 1 meter box, if you break down into 1 nanometer, it will closely make up a land of 6 3 zeros, then 3 zeros, then 3 zeros meters square. So that much area will be exposed to the surroundings. So this exposure to the surroundings is certainly making this material more efficient, and certainly making it change the properties that it has. These properties can change at that scale. So you can see that the idea is very clear. 1 meter cubical box can be converted into practically speaking, very, very large amount of area. And exposing that area to the surroundings will certainly make difference in terms of the properties of these materials. See here, a simple example I have quoted down. You can see this is gold, okay? The bulk of the gold, it has a yellow color, and it's certainly used as an ornament in our traditions, in Indian traditions, and you can see if we take the nanoparticle of the gold, if we break down this gold to its nano state, its color changes. So you can see what is gold, what is identified as gold is not gold, does not have the same properties when you take the same thing to the nanoscale. You can see the color is totally different. The color is not golden at all. So if I give somebody a nano patch of gold, you will say, come on, this is not gold, because its color is not yellow. So the idea here is that when I take the gold particles to the nano state, to some particular range of nano state, the color of the gold changes. Now you can see we have these sheets of carbon atoms, and the tubes that are made out of these sheets, these are atomic. The width of these sheets is nearly 1 atom. And when you mold down them into some curvatures, we call them as nanotubes. And in these sheets, at every point, a carbon atom takes the part, right? So this material is made of carbon atoms. Now these carbon nanotubes they're 100 times stronger than steel. They are flexible. They have unique electrical properties. See, the point is they have electrical properties. If generally we talk about diamond and graphite, both of them are made of carbon atoms, but they behave as insulators. But when we design them at nanoscale in terms of the carbon sheets, which is probably known as graphene, when we mold down them into some characteristic geometry, they become conductors. they conduct electricity. Now their electrical property changes with the diameter, twist, and the number of walls. See, by tilting the carbon nanotube, we find there is change in the properties of these materials, which is not the case when we talk about the classical metals, the classical conductors, right? If I have a copper wire, it is going to conduct, okay, and it will conduct in all positions. So here they can be either conducting or semi-conducting in their. So now by just twisting, by just tilting the carbon nanotube, you can change its property. Firstly, maybe for the sake of argument, first they were behaving as conductors, now they are behaving as insulators by simply tilting the geometry of this carbon nanotube. So we can understand the sensitivity of the matter here. We can understand that how things change at this very nanoscale. Now you see, a neuron, okay, everybody knows that we have the brain, and the brain is made of some cells. We call these cells as neurons. So all the information that we probably have, we receive or we send, and we send it through the neurons to the brain, and possibly the size of the neuron tissue is comparable to the nanoscale. Now it has to be comparable to the nanoscale, and because we can understand there's a lot of flexibility in our thoughts. There's a lot of things going on in our mind. We cannot calculate them. To be precise, if I take 1 centimeter cube of the brain, the number of neurons it has, it may exceed the number of stars that are present in the whole universe. So we can understand that there is a hell of bunch of neurons in our brain performing their duties, performing their job by virtue of internal characteristics and the environment that they are reacting with. Now, neuroelectronic network interface nerve cells with semiconductors, okay, possible applications in brain research. So if you have to make something that can certainly make an interaction with neurons, you certainly want a nanorobot, right? Now the nanorobot can do its job only when its size falls in the domain of the size of the neurons. So the application of nanotechnology in making research in the brain, that's clearly possible. You can do that, and people are doing around the globe, preparing the networks and making them ready for the examination and doing all the research that is possible.